So let's get started. So I think we have now all the tools to write the rotational dynamics. And the rotational dynamics, as I said, is a time rate of change of the angular momentum. And the angular momentum is again a vector with the inertia matrix, which is written in the body axis system. I have to say it where it is written because in every axis it will change, right? Times omega b, which is now with respect to the inertial frame that's in the body axis system. Okay? All right, so we have to take the time rate of change with respect to the inertial frame, which means someone looking from the inertial system, looking at our airplane, and the body axis system is rotating. Right? We have to take the derivative, the time rate of change of this hb with respect to this fixed coordinate system. And hb is at the end, it's a vector, right? It's a vector hb. That's a vector. It's the angular momentum of the airplane. It's a vector like any other airplane. So since it's a vector like any other airplane, I have to treat it like a vector like any other airplane. So this is what we are going to do. We are going to take dHb dt in the inertial, in the fixed coordinate system. Derivative is in the fixed coordinate system. And because the body axis system is rotating, I know how to take the derivative of this, right? Body axis system is rotating. The inertial coordinate system is not rotating. And I'm trying to take the derivative of a vector which is written in the body axis system, but the change I'm looking at is with respect to the fixed coordinate system. What do? I use the Coriolis theorem, right? So it would look like this. It would be h dot body plus omega body cross product h body. It is just like looking at the velocity. This is just another vector, like the velocity vector. It's another vector. It's written in the body axis system. I'm looking at the time rate of change with respect to the fixed coordinate system. And this is exactly what the Coriolis theorem is about. Okay? Now this one here, hb dot. If you get confused with this part, really you need to go back to the Coriolis theorem and try to understand again what this is about. hb is just another vector. So let's look at the time rate of change along the axis. The time rate of change along the axis is, since this is hb, it would be hb dot times omega b plus ib times omega b dot, right? Time rate of change, the chain rule here. Okay, first question. Does the inertia of an airplane change in time? How does it change? If the fuel changes, if the passengers move, and all this. Let's say the fuel is constant, passengers don't move, all mass properties are the same. Does it still change? They are very tiny. Let's ignore the control surfaces. Will they change? Will it change? The answer is it's almost zero. The change is very small. Okay? Of course, assuming if the fuel is constant and all that. If I would write the inertia matrix, let's say in a vehicle carried coordinate system, would it change during flight? Why? Because the direction of the coordinate system keeps changing, right? I mean, the coordinate system's direction doesn't change, but the airplane's nose will change. I mean, the airplane's angular position will change. So if this is north, east, and down, and the airplane starts doing that, right? If you're flying like this, the x direction is this way, so you have an inertia matrix for that. If the airplane is rotating like that, now the x inertia matrix is, the x direction in the inertia matrix will be this axis, so it will change the inertia. The inertia matrix will change. Do you understand it or not? You're looking empty. Yes. If you don't understand, just let me slow down. I mean, I hate to tell you something and you don't understand, and what's the purpose of the class, right? Do you understand it or not? If you write the inertia matrix in the vehicle carried coordinate system, as the airplane moves like that, at each instant the x will point in a different direction along the airplane, and therefore it will change the inertia matrix. The only coordinate system for which the inertia matrix is approximately constant is the body fixed coordinate system, because it moves and rotates with the body. Okay? And this is the reason why we write everything in the body axis system. Otherwise your life would be very difficult if you had to calculate this at every instant in time. Okay? Think of the wind axis system. If I would write everything in the wind axis coordinate system, because if you think about it, since lift and drag are written in the wind axis coordinate system, it would make sense to write everything in the wind axis coordinate system, F equals ma. I could write it in the wind axis coordinate system. The problem is, if the wind blows from this side, look up here, if the wind blows from here, then you need the inertia matrix with respect to this coordinate system, x, y, and z. If the air moves from this direction, you need the inertia matrix for this, x, y, and z. Right? So therefore we are fixing the coordinate system so you don't have to calculate the inertia matrix over and over again. And I told you it's not easy to calculate the inertia matrix even for one coordinate system. Forget about a coordinate system that's rotating. Okay? With respect to the airplane, of course. So therefore we are using the body axis coordinate system here. Mostly, I mean, we have other good reasons too, but this is a very big reason why we do that, because the inertia matrix is constant. Calculating IB dot would not be easy, and at each time instant you would need to change, look at that change. So, omega B is P, Q, and R. And what about the moments? The moments, the external moments that act on the airplane, what are they? We have the names for them. They were L, M, and N. So, are there moments coming from the weight, like in the translational? The answer is no, because if you write everything around the CG, then the weight does not introduce a moment, right? So these are still the aeropropulsive moments, but no moment is coming because of the weight, because everything is written around the CG. So then we have pretty much everything. So then looks like I can write the whole thing now. I can write this thing, the whole equation. So it will look like this. L, M, and N is equal to IB times P dot, Q dot, R dot, because here you have P dot, Q dot, R dot, right? This is that part, plus P, Q, R, cross product, inertia matrix times P, Q, R. That's the big one. Okay. So this one here, this part here, this is here, this is here. The external moments written in the body axis system. This part here is HB dot, and this part here is omega B cross product HB. Okay, And this one as a total here is dHb dt, all written in the inertial, with respect to the inertial coordinate system. So this is that. Understand? Rotational dynamics. Momentum, time rate of change of the angular, moments, time rate of change of the angular momentum. We use Coriolis theorem and then write the appropriate equations, and this is that. Any questions? Now you have to open this up and write everything in one line. Take the cross product and write everything in a line. Any questions how I got here? All right, so let me write down the first line. Okay, I'm going to take the cross product, I'm going to take this multiplication, write the first line. The first line looks like this. L is equal to, it's going to be a long line, Ixx P dot minus Ixz R dot plus PQ minus Iyy minus Izz QR minus Iyz Q square minus R square minus Ixy Q dot minus RP. That's the first line. How do you like that? Okay, rotational dynamics. This is our fourth equation, right? First in the rotational, fourth in the 6-Prof equations. The second one looks like that. Iyy Q dot minus Ixz R square minus P square minus Izz minus Ixx RP minus Ixy P dot plus QR minus Iyz R dot minus PQ. And the third one looks like this. N is equal to Izz R dot minus Ixz P dot minus QR minus Ixx minus Iyy PQ minus Ixy P square minus Q square minus Iyz These are his three equations. This is what we call the three degrees of freedom. 3 degrees of freedom. Rotational dynamics. And I will call these equations number 2. The first ones were the translational dynamics, and this is now the rotational dynamics. Those were the translational dynamics here that we had at the beginning of the class. And these are in the rotational dynamics. And this is again in the body x-axis, the first line. The second line is in the body y-axis, and this is in the z-axis. So, if you look at these equations, let's start here. Let's look at the translational dynamics first. Okay, let's forget about this. Look at the translational dynamics. A few things I want to mention is, if the airplane has a symmetry axis, which means the product of inertias here, this one, this one, this one, this one, this one, and that one, they would be 0 if it has a symmetry axis and if it's a typical airplane, right? Because the product of inertias, if it's symmetric like that, they would be equal to 0. If it's not symmetric, you have to include them in the equations. Okay, that's number one. Number two is IXZ, this one here, and that one, and this one. There might be small, okay? As I said, as we looked at, right? You're looking from the top and the bottom. We looked at it in the last hour. They might be small. If they are small, if they're kind of canceling each other and stuff like that, these terms might also go. Okay? Those terms might also go. Understood? Okay. Now, one more thing. Look at the first line. L is what? It's the moment in the body x-axis, right? It's a rolling moment. It's this. What is Q? It's pitching. What is R? It is yawing. So typically, if you give an L, right, you shouldn't really get a Q and an R, isn't it? Q is pitch, rho is yaw, right? So if you had an airplane that is not allowed to pitch and yaw, then these terms would be equal to 0, right? But they are not, because it's a three-dimensional thing, right? But let's say it is restricted to only to roll. Then there's no Q and R. So this would also go to 0. If it was restricted, it is not restricted, it will do Q and R. But let's say it is restricted to Q and R, right? It cannot do Q and R. So roll will only give you P, not Q and R, let's say, for a moment. Then this term would also go. What would you have? You would have L is equal to IXX times P dot. And this is a simple equation you probably learned in dynamics. Moment is equal to inertia times angular acceleration. P is velocity, P dot is acceleration. So this is, if you have an airplane, okay, or forget about the airplane, let me just remove the wings. If you have something like that, and it is not allowed to do this or that, it can only do this, okay? So moment in this direction, IXX will give you the angular acceleration in that particular direction, okay? So you move it in that direction, it will just give you the angular rotation, the angular acceleration in one direction. So that will be the simplest form. Moment is equal to inertia times angular acceleration. But if you do this in 3 dimensions, then these are the equations. Okay? And if this thing is not symmetric, okay, and it is allowed to move in every dimension, in every direction, so these are the 3 equations. Is that okay? Any questions? So now as an engineer, you have to make the decision which ones you want to keep as 0 or which ones you don't want to keep as 0. That's why people are going to pay you money. Anyone can open the book and copy these equations. That's not the problem. The problem is which ones are you going to take 0, which one is okay to make that assumption to take it as 0, right? All right, one more thing. These three equations, they are differential equations. There's a P dot, Q dot, R dot. So it doesn't look like that, but they are differential equations. In fact, I have a few dots. I have not only one dot, I have P dot, I have R dot here, and I have Q dot here. So I have all three of them in one line, you see. Same thing here, R dot, P dot, Q dot, R dot, Q dot, and P dot. So these are differential equations, and they are not easy to solve because they're all connected now. I cannot write them in a nice and clean form like I have written it over here. They're all kind of interconnected, right? They're kind of interconnected. So if you want to solve this, you have to solve this together. If you want to solve these three, then you still need the information of P, Q, and R, and they are coming from here. Okay? So you cannot really solve these things independently. P, Q, and R, they are coming from these equations. Theta, phi, and psi are functions. They are also of P, Q, and R. They are also coming from here. So as time goes by, these things and these things, they need to be solved together. That's why they are called sixth of rigid body dynamic equations, and you have to solve them together. These three equations, as I said, they are called Newton-Euler equations. So we already mentioned last time that the aerodynamics here is in X, Y, and Z. And where is the aerodynamics here? Where do I get the aerodynamics here? What makes this an airplane? It's L, M, and N. So X, Y, Z, L, M, and N, they will change depending on the airplane. Okay? And this is where you have all the effort to calculate lift, drag, moments, and things like that. All the things that you learn in aerodynamics, they are here to calculate them. Once you calculate them, then you can tell what the airplane is going to do in future, and you can plot graphs of what the airplane will do as time goes by. So at the end, you have 6 differential equations. You start with an initial condition, and you can propagate this in time like we did for the pendulum. Okay? We wrote a function. It was simple. This thing you cannot do with the function if you don't do simplifications. What you need to do is you need to do some numeric time propagation, okay, and then see what happens in time. Any questions about these? These are the 6 degrees of freedom, rigid body, dynamic equations. And we call them Newton-Euler equations. You understand where every term is coming from and what they are. Okay, so of course we can make simplifications. The biggest simplification was, of course, it's not even a simplification anymore. This is true. This is equal to xy is equal to 0. And I'm going, just to make things simpler, I'm also going to say xz is also approximately equal to 0, and this is of course an assumption, but not a bad assumption, okay? If you make that assumption, then you will get a simpler set of equations that look like this: Lixx plus Iyy minus Izz Qr divided by Ixx, and that would be Q dot is equal to m divided by Iyy plus Izz minus Ixx Rp Iyy. And R dot will look like Nizz plus Ixx minus Iyy P Q I Z Z. So if you want to make a quick approximation, or it's not a bad approximation really. I mean, these equations are not bad of approximations. You could actually use these 3 equations along with these ones, then you have 6 differential equations that you can better deal with, right? The assumption is that the product of inertias are equal to 0. You see? U dot V dot W dot P dot Q dot R dot. Perfect. So we have a great set of equations. Okay, so we have our differential equations for our airplane, right? We have our differential equations for the airplane now. Well, the next question is, once I have the differential equations, what do I do? The first thing I'm really interested in is I'll look at what did we do after we found the equations of motion for the pendulum? What did we do? Huh? We would find we did the equilibrium points, right? We looked at the equilibrium points. That's the first thing we did. We looked at the equilibrium points, and then we linearized it around the equilibrium points. Okay? So, what would be the equilibrium point for this set of equations? The equilibrium point for this set of equations would be U dot is equal to V dot is equal to W dot is equal to P dot equal to Q dot equal to R dot is equal to 0. That is the equilibrium point for these equations. Okay? So I need those numbers for my for my equilibrium point. Okay, so let's do that. But I have to define now, let's ask here, let me start here. Setting these equal to 0 will probably have a number of solutions here, right? It doesn't have only one solution. I mean, what I'm going to find is I'm going to find U, V, W, P, Q, R, X, Y, Z, L, M, N, the trim point of an aircraft is also an equilibrium point for the aircraft. Let me give you the definition. definition. A trim point let me put this in quotes. A trim point of an aircraft is a state where all resultant forces and moments are equal to 0. A trim point of an aircraft is the state where all resultant forces and moments are equal to 0. Now that's a definition. Okay? This is what we mean when we say a trim point. If all resultant forces and moments are equal to 0 for an airplane, I call this a trim point. What would the airplane do? What would it be doing if all forces and moments are equal to 0? Constant speed, right? Or constant rotation, right? One of the constant altitude, which means still constant speed. Does it mean constant altitude? How about this one? Okay, let's start here. Airplane constant velocity, is this in trim? Constant velocity, is it in trim? Why not? Does what? No, it's going constant. Going straight, constant velocity going straight. Trim? Yes, it is in trim. Right? When forces and moments are equal to 0, force equals 0 means acceleration is equal to 0. Velocity is constant. Right? So it will go with a constant velocity, and this would be a trim. Is this in trim? Constant velocity going up. Yes? No, why not? Lift is bigger than weight. Is lift bigger than weight? How can you say that lift is bigger than weight? If lift was bigger than weight, it would just go, it would accelerate. At the beginning it was bigger than weight, and then it became constant. When it's constant, velocity is constant, which means forces are equal to 0, isn't it? How about this airplane? Constant velocity going down. Is it in trim? Yes, it is in trim. Is it falling down? Yes. Don't tell me the lift is less than weight and it's falling down. If lift is less than weight, it means there is a force, and if there is a force, there is acceleration, which means it is going faster and faster. The lift must be exactly equal to weight if it's constantly going up. I mean, not in terms of direction, right? This is lift, this is weight. But all forces, add them together, they must be equal to 0 if there is no acceleration. Is this airplane in trim? Yes, no. Hurry up. How come you say yes? Is there acceleration? Yes. If there's acceleration, is there a net force? Yes. So is the resultant 0? So is it in trim? No. Okay? How about this airplane? Is it in trim? No, because it's rotating, right? Is this airplane in trim? Yes. Is this airplane in trim? Hurry up. Is this airplane falling down like that with constant velocity? Is it in trim? Yes. The resultant force is 0. If the velocities are constant, there's no acceleration, forces are equal to 0. It always feels like, oh, this is falling down. It cannot be in trim. Oh my God. The velocity is constant, so it is a trim condition. Velocity is 0, not 0. Acceleration is 0. Therefore, the total forces are equal to 0. Okay? It doesn't matter if it's falling down or not. Airplane falling down like that, constant velocity, is it in trim? Yes. Some people will say, oh, the airplane cannot do that. Yeah, it can do it. Assume it is doing it. Would it be in trim? Yes, it would be in trim. Okay? Airplane falling down like that, would it be in trim, constant velocity? If it was constant velocity, yes, it would be, right? So this is what we mean by trim. Constant resultant forces, the acting forces and moments, the total acting forces and moments, if they are equal to 0, that includes the weight, okay, then we call this aircraft in trim. How many trim points does an airplane have? Infinitely many, right? You could go, every different speed would be another trim point. Every different speed would be another trim point. Every different speed would be another trim point, okay? So this is what we call trim. So from an equilibrium point of view, but from an equilibrium point of view, we also need that, right? We also need this, okay, from an equilibrium point of view. All right, so let's choose one trim point and analyze it. This is what we are going to do now. Let's choose a trim point and analyze. Okay? And the trim point that I'm proposing us to use is the steady a trim point of an aircraft is the steady level flight condition. Steady level flight condition. So in steady level flight, that's steady level flight. Look up here. When you're not turning and you're at constant altitude and you're going straight in air, that is a steady level flight condition. Okay? So typically if the airplane is in symmetry, you don't have a roll angle. The roll angle is 0. And you might have a pitch angle because you need angle of attack. And you might be flying like that, right? Constant velocity, no rotation, nothing. So this is what we call a steady level flight. So this is the simplest flight condition, of course. And this is a trim condition. So we are going to look at that trim condition. In steady level flight, obviously because it is in trim, these things, there's no acceleration, right? I mean, we know that. How about P, Q, and R in steady level flight? What is P, Q, and R in steady level flight? 0, right? 0. So this is what we call at a trimmed steady level flight. P, Q, and R is equal to 0. How about phi? I just said that. If it's a symmetric airplane, it must be 0. How about theta? Is it 0? Not really, right? There is probably an angle of attack. How about U? Would that be 0? No, of course not. How about V? Would that be 0? Could be if there's no side slip. If the airplane is not going like that, look up here, if the airplane is not going like that or has a side slip, then it must be 0. If you're just going straight, V must be equal to 0, right? So V is equal to 0. How about W? Not 0, right? You might have an angle of attack. W is angle of attack. W doesn't mean this. If you're going like that, you have a lot of W. Okay? So W is W0. Okay? So this is that. All right. So in trim then, we can look at the first equation. Look at u dot is equal to RV minus QW plus x divided by m minus g sine theta, right? First equation here that we found. So in trim, or in steady level flight trim, of course, this is 0, right? R is 0, Q is 0. And we have this thing. Is x 0? Not really, because x must, the mass is, the weight is not 0, x is not 0. X doesn't have to be 0. X is not the total force. X is only one of the forces. There's also weight. X is only aeropropulsive force, right? It doesn't have to be 0. I mean, it's like saying in level flight lift is equal to 0. Is lift equal to 0 in level flight? No. Lift is counteracting the weight. Okay? So lift is not equal to 0. So therefore, x cannot be 0. X is the aeropropulsive force. So therefore, x is not equal to 0. Mass not, g sine theta no. So what you have here is that x divided by m is equal to g sine theta. So x must be equal to mg sine theta in trim. Which basically means that the aeropropulsive force has to counteract the weight. Okay? It has to counteract the weight. And this is, of course, in trim, right? We know these are trim numbers. So in trim, trim. That all means it's in trim. So x0 is the aeropropulsive force, aeroprop force in trim. And so is theta 0, okay? They are all in trim. Okay, let's look at the second equation. And let's try to be a little faster here. Let's look at this one, the second one. V dot is equal to 0, P 0, R 0. This is not 0, and that is not 0. So you have, what do you have? Y over m minus g cos theta sine 0. What is sine 0? Because phi 0 is 0. This is 0. So y0 is equal to 0. So the side force must be equal to 0 in trim, which makes sense. If you're going straight like that, the side velocity, there's no other in the side velocity other than the side, the aeropropulsive force, and that must be equal to 0. There's no weight on the side, right? How about the third one? Can you tell me what is z0? Zero, 0, 0. Cosine 0 is what? 1. So z0 is equal to minus mg cos theta 0. Is that correct? Okay. Wonderful. So we have the aeropropulsive forces for the trim condition. Now let's look at the rotational dynamics. Rotational dynamics. In trim, let's look. L0, right? It doesn't have to be 0. Let's see aeropropulsive force. P dot is 0. R dot 0. P 0. Q R 0. This is 0. This is 0. This is all 0. How about M0? Q, P, R, P, M 0. Here are. So in steady level flight, this is basically what we have, right? in steady level, trimmed flight. So, what we're going to do after this is, since we know the equilibrium point now, we're going to linearize it around the trim points and see what we are going to get. Of course, we are going to get an A matrix, right? We're going to get a big A matrix once we linearize it around this equilibrium point. And this is an equilibrium point, right? You're going constant. U dot V dot W dot is equal to 0, P dot Q dot R dot is equal to 0. According to our equations, this is a trimmed, this is an equilibrium point for the airplane. The trim point is also the equilibrium point, right? Or all trim points are equilibrium points because U dot V dot W dot, P dot Q dot R dot are equal to 0, and by definition they are equilibrium points. So now we found an equilibrium point, we are going to linearize it around the equilibrium point. If I linearize this around the equilibrium point, I will find an A matrix. And if I look at the eigenvalues of the A matrix, what will it tell me? It will tell me what will happen if there's a disturbance to this airplane. Will it come back to the equilibrium point? Or will it do that? Okay? It's going to be quite exciting. Because when you have a gust in the air or a turbulence, will the airplane come back to the equilibrium point, or will it do that, or do this, or do that? Right? So that's what we're going to do next time. Now, for just 1 second, I think we are in the middle of the semester now, okay? And slowly students might drop coming to class, but we are not over yet. Okay, it is not a good idea to stop working in this class because we have done the fundamentals, but the real stuff is still to come. Okay, so I'm seeing people coming less to classes and everything. Not a good idea, believe me. All right, just a little caution. So see you next week.